So here's a figure showing what we ended up with the setup for the mola simulation lab. Again, the idea was to simulate how the Mars Global Surveyor, using the mola instrument, could send laser pulses from orbit down to the planet Mars surface and have the laser pulse bounce back, and use that time to calculate the distance from orbit to whatever the land surface was, and therefore figure out how high that land surface was. We've flipped things upside down, and the floor actually represents the orbit of the spacecraft, and that tack strip for putting up posters in the hallway represents some basement part of Mars, and we taped our profiles upside down, so that rather than having to drop the ping pong balls and measure precisely when the ping pong ball passed the line for the profile, we instead have the ability to drop the ping pong ball from the profile and figure out the distance by the time it takes the ball to hit the floor. So first, before we start doing any measurements at all, we have to calibrate the velocity on the ball drop, the ping pong ball drop, and that's what those calibration measurements are that we'll see in a minute. So each of the groups dropped the ball from the poster strip, measured how long it took to get to the floor, and did that multiple times so that there would be replicate values. And essentially, this distance from the tack strip to the floor is known, and the time it takes the ball to drop is known, so we can calculate an average velocity for that ping pong ball drop. In general, this distance was, for most groups, just a little bit less than 2 meters, a little bit less than 200 centimeters. So then for the actual data collection, instead of dropping the ball from the height of the poster strip, the group started out at 0 and dropped the ball from the drawn profile. And again, it would drop to the floor, but because it's a shorter distance, on average that should be a shorter measured time. And the idea would be to use the time that it takes the ball to drop here and the average velocity to figure out what this distance is. And so if you can calculate what the distance is here, and you know what the distance is here, then by subtracting, you can get the distance here, which would represent the elevation data if we were actually doing this experiment in orbit. Okay, so here's the actual data for one of the groups. And you can see that they measured the height of that poster tack strip to the floor at their site and got 198 centimeters, so just under 2 meters. And they did the 5 calibration drops. So dropping that 198 centimeters, one time it took 0.8 seconds, the other time it took 0.6, 0.8, 0.7, and 0.7. You can see that they measured the height from the strip down to the floor with 3 significant different digits, 198 centimeters. Clearly calculating the time of the ball drop is the less accurate measurement. They've got essentially 0.10ths of a second, so 0.8, 0.6, 0.8, 0.7, 0.7. There's barely much more than one significant digit there because they're not going to be able to measure 0.83, 0.84, 0.87, given what they're, how they're collecting it. But anyway, with 198 centimeters and these times, they have calculated these individual velocities. You average it all together, you get 2.778 meters per second, or more useful for our purposes here would be 278 centimeters per second. So this average velocity then can be used to take each one of these measured times. So again, they went through and dropped a ball from the profile line at the 0 centimeters along the transit, measured 0.5 for it to drop, and then along at the 10 centimeter point along the transit, dropping the ball from the profile line rather than the poster strip line. They got a 0.4, and then at 20 they got 0.5, and then at 30, 0.6, and so forth down along the profile, and then did it again, and a third time, and a fourth time. And you see, of course, that there's variability from time to time. So none of these measurements individually are, completely accurate, or we don't actually know if they are or not. But by looking at the different values, we can, get an idea of how variable this timing measurement is. So, given those times and this 278 centimeters per second, if the ball drops half a second, let's just say 280, then that half a second would represent 140 centimeters for dropping from the profile to the floor, and we know that the total distance is 198 centimeters, so we would guess from this measurement that whatever was drawn on the piece of paper they were measuring from would have had a height of 58 centimeters above the bottom of the paper. You can do the same thing with the second measurement. 0.4 second drop means would mean that it fell. The ping pong ball fell 112 centimeters, which is 86 centimeters less than that total length. And then 0.7, we get 196 centimeters, which means we would estimate that the height of the profile from this measurement was 2 centimeters, and we have another measurement of 0.5, so we would guess that the ball dropped 140 centimeters, which would mean that the profile was 58 centimeters above the bottom of the paper. So we have basically 4 estimates of how high that profile is above the top of the paper. We could then average those together, and from those we get an average of 51 centimeters with some clear variation around that mean. We have measured values everywhere from 2 centimeters to 86 centimeters. So this is going to be 51 centimeters plus or minus quite a bit in terms of the standard deviation. So in terms of turning in your data analysis and graph, basically what we're looking for is a table where you've got the locations along the profile where the sampling took place at 0 centimeters, 10 centimeters, 20, and so forth. And then what you need to do is to take the ping pong ball drop time and the average velocity, multiply them together to get the estimated ball drop, and then subtract that from the total height to get your individual estimates of how high that profile that was drawn by the other group was. And you should have anywhere from 1 to 4 times to use to calculate those estimated profile heights. And then just you can take the simple arithmetic mean by adding the numbers together and dividing by how many numbers there are. In this case, the average was 51. And ideally, you would also want the standard deviation. And so for for plotting the data, you would have the profile distances along the x-axis and the estimated height, average height of that profile at each of those locations along the y-axis, 10, 20, 30, 40, 50, 60, 70. And then the average for the 0 centimeters is at 51. And I haven't calculated the averages for others, but let's say the next one has an average of 45, and then there's an average of 18, and then an average of 15. You get the point. You can use those reconstructed profile heights from the set locations on the profile that we're taking it, and plot the values and draw the curve, and then ideally the curve you would infer from those measurements of ball drop times should look like the profile for the group you've got, and should also be about the right scale. And you would turn in your data table and your graph when you're submitting the assignment.